Recording is rolling. It's Tuesday, March 4th. Right, so SAT, of course, coming up in a couple of days. Most of you guys are taking the SAT, and you guys know on Google Classroom, I posted the list tells you exactly where to test. Here's relocation, because there are some of you guys who are not taking the SAT, but the SAT is going to be in this room. So, of course, we're not going to have physics on Thursday. So here's relocation for my first 4 classes. And if you want to know where are your other classes relocating, that file is also on Google Classroom. Here, show you guys here. All right, so here's some things I posted recently. Got volunteers opportunity, got my updated book. Here's SAT list and relocations all right here. Of course, here's yesterday's class video. Oh yeah.
Are they gonna call attendance in this class or like, can I just dip after the SAT?
Yeah, you have to be on. That's cool. Yeah.
Okay.
Yeah, all right. Yeah, so if you're taking the SAT, you have to stay in your SAT testing room all through 4th period, and then after that, you just go to 5th period. Okay, so we're gonna do. Okay. All right, so before we get to our main stuff today, here, let me fill you guys in on some stuff from my other classes, because there's some stuff that AP does not test you guys on that my other classes are learning. So we're going into optics. You guys see some green banner posters hanging around. Of course, you guys have these anyway, but just to fill you guys in, there's this law of reflection. If you have a mirror, you guys see reflective surfaces could be a mirror. Right? Now, this candle flame can be sending out a billion different light rays, all different directions. But if you pick one particular light ray, like a laser light, it will always bounce off so that relative to this normal line, this angle of incidence always matches this angle of reflection. That's called law of reflection. Okay. Now, what if you don't have a flat mirror though? Oh, and you can show, you can do this with a bunch of light rays and show where the image shows up on the other side. I'll show you guys sort of some examples later. Okay. What if you don't have a flat mirror? Like, what if you have a curved mirror, like a giant mirror ball, right? Something like that, like a giant shiny bowling ball. Okay? So the law of reflection still applies. I know it's kind of hard to tell. There's a faint line here coming from the middle of this globe shape. Okay, so if I have a laser light going like this, say like what if I was aiming right at the center? Of course, it would just reflect straight back. But what if I offset this a little bit? Boing. Okay, well, it's going to bounce off so that this laser light would align with what's called a focal point. It's this focal point right here. Okay, and where's this focal point? Well, this focal point is halfway between the center and the surface. Right, so this focal length, which is this, which is also this focal length, ends up being half of the radial size. Right. Right. Now you put those ideas together and figure out what's going on with the funhouse mirrors. Right. So now here's a regular plane here, and you can follow as many rays of light as you want. But see, this one can bounce straight back and forth. This one coming through his head will bounce off according to the law of reflection. And if you extrapolate backwards, it looks like this ray came from back here. It looks like this ray came from back here, and the top of 70 degrees here. His feet are still on the floor here. So, oh, look at that. If you look at a flat plane mirror, you see an image of yourself just on the other side. All right, so I see that. Okay. Now, what if you look in the backside of a spoon? Ooh, guys, in the backside of a spoon, does your reflection look kind of yourself just smaller? Right, look a little tiny. Right. Now this one, there's not a lot of variation, so you pretty much always get this as a result. So you can use that same technique. Right. So these are ray diagrams. That's what these are called. These are called ray diagrams. So you figure out where the reflection's going to be. Where's the image? Okay. There's also an equation that goes along with this. And this equation goes exactly hand in hand. So 1 over focal length equals 1 over distance object plus 1 over distance image. So distance object is the distance from the object to the surface. So I'm always going to have that as a positive value. Now the image, maybe that's what we're solving for. It's like where does the image show up? Right? And the focal distance, right? Well, for the curved mirror, it's easy to see. It's this distance right here. So we're going to measure that. Okay. Now that's going to be negative because it's on the opposite side from the object. Okay. Right. Now, guys, what about for a plane mirror? What do you think the focal length would be for a plane mirror?
Same as the distance.
Fair. Fair. Like, how big would the sphere have to be so that you think the surface is actually a plane? The radius would have to be how big? Yeah, that's right. Like infinity, right? And then what's half of infinity? Still infinity. Hey, guys, what's 1 over infinity? Zero. Right? If you buy a lottery ticket and you have a 1 in 200 million chance of winning, it's basically 0, right? Okay. Guys, watch this. Suppose this guy's standing 3 feet from the mirror. 1 over 3 plus 1 over what equals 0? -3. Oh, and look where the image is. It's -3. Right. Right. And then you can do the same thing this way. Right. Now, what if you take the spoon here? You guys see the backside of the spoon, and you turn around, make it like a cosmetic mirror. Oh yeah.
So why don't they just write 0 instead of infinity?
Well, it was 1 over infinity, which is 0. Yeah. Right. So 1 over infinity is 0, right? Okay. Right. Yeah. Right. No, this formula will work for all these different types of mirrors, though. It could be this plane mirror, it could be this convex mirror, it could be these concave mirrors. Now, if you flip the spoon over, you get like a cosmetic mirror. Well, you get different scenarios depending on where is the object relative to the focal point. Okay, so if your eyeball is inside that focal distance, it's effectively a cosmetic mirror. Like I think I got one right here. This mirror has a little bit of concavity to it. You know what other mirrors have a little bit of concavity are all the major telescopes today. So, for example, the Hubble telescope uses a mirror for reflecting ones. Actually, that's Isaac Newton's invention there. Okay. But if you back that mirror up too far away, then you get what's called a real image. You guys see that? Has anybody had a chance to see this yet? No, it's hard to put it under the camera, right? But you can kind of see it. Right. So there's this actual plastic pig down here, and there's a couple of parabolic mirrors. You guys see they're both concave? Is it? Okay. And if you're just at the right angle, this works better in real life than on camera. Right. You can see this real image of a pig. It looks like something you can pick up, but it's not really there. Okay, so first I'll put this out, put it down, okay, get a chance to see that. Okay. So those are all examples of reflections. Now, what I'm doing in my classes later today, my other classes is we're getting into refraction. You guys know, like you put a straw in a glass of water, it looks like it's all bent, but it's not really. Right? You take it off, the straw straight. It was never bent at all. Right? Okay. So light will slow down in water compared to a vacuum or compared to air. Okay. And because it slows down, you can go through a process and shows that it's going to refract, right? It's going to change angle, it's going to bend. Okay. And there's an equation that tells you exactly how much it's going to bend. It's called Snell's law. Okay. And that's related to how much light slows down in water. So n index of refraction could be what's the speed of light in a vacuum, like 3 times 10 meters per second. What's the speed of light, say, in water? It's going to be significantly slower. You take the ratio, you get index of refraction. So for water, I think it's like 1.33. For certain types of glass, it's close to like 1.5. Okay. And then that will dictate the relationship between these angles. Here's Snell's law, you put it all together. So here, I've got a flat lined up from my other classes. You got laser light, you got prism, and oops, see if I get this right. Is that showing up on camera? Okay, well, okay, it's kind of, right? Can you guys see the speed of light going out this way? Okay, because it looks like it had to double refract, going from this air to this glass and this glass back to this air again. You guys see it refracting out here? Okay. So if you measure those angles with a protractor, you can determine what is the index of refraction of this material, like how much does the light slow down? Right there. Okay, so that's a quick rundown that's going on in my other classes. Okay, but you guys got some notes out because we're going to do some Atwoods today. All right, you guys ready for some? Oh, yeah. Well, I said, okay. Right. I'm saying double because the laser light goes from the air to the glass. That's one refraction. You go from the glass back out to the air again. That's 2 refractions. So it bends here, but it also bends here. So every time it crosses the medium. Yeah.
So if it's slowing the speed of light down, does that mean if you get something that refracts enough, you can like measure the speed of light and make it the same as however you want? You can make the speed of light really slow.
Yeah. I remember reading some articles of scientists were able to slow it down significantly to like walking speed or something.
So then could you make it faster?
Well, the fastest that light will go is just through a vacuum, and you can't really make it go faster than that. When you get to theory of relativity, there's you basically can't make light go faster than what it is through a vacuum. Yeah. All right. All right. So you guys get so far. All right. So yesterday, near the end of class, you guys saw this elevator. I had you guys derive this. You guys remember that you derived this? So what's normal force on scale, or this could be the tension in the cable holding it up, I think. Okay. And that's about to be helpful. Right. Oh, here's an elevator either accelerating up or accelerating down or not accelerating in the middle. Okay. Right. That's about to be helpful for these Atwoods. We're going to do a bunch of Atwoods today. Right, you guys ready for some Atwoods? Atwood time. So Let's start with the classic double elevator. Okay. Put a block up here, block down here. Okay. Oh, let's say this mass is 3 kilograms, and this one's 4 kilograms. Okay. So some things that I might want to know. What is the acceleration? Acceleration of the system. Okay. Or that might be worded, what's the downward acceleration of the large block? You might say that way. Okay. I want to know what is the tension in the string, the connecting string. Say how fast after, let's say 1 second. And how far does one of these blocks move after 1 second? You know what? Let me throw another one on here. How fast after, I'm going to put some distance here, but I'm going to leave this blank because whatever the answer is to this third question, this fourth question, how far? Right. I want you to see that these last 3 connections are all connected. Okay. So let's figure these out one at a time. So I'll solve this off screen. You guys solve it on your paper. Okay, let's see if we're all getting the same answer here. All right, I've got the answer on my calculator screen. Okay. Well, for the first question, guys, the first question is what's the acceleration? Say what's the downward acceleration of the large block? What's the upward acceleration of the small block? All right, so I'm looking at the answer on my screen.
Oh, I got it.
Oh, you got it?
I think it's like 7.
Try again. All right, what's the downward acceleration of the large block? The upward acceleration of the small block? Generally, the acceleration of the 2 block. Does anybody know the acceleration? Oh yeah, what you got? Here, I'm looking for a number because I gave you guys 3 kilograms versus 4 kilograms, right? Okay. Oh. Now, guys, whenever you see that question, what is the acceleration of something? There's one of 2 entry points to answer that. One is if you have a bunch of kinematic values, like, oh, the car went this distance and this time and to a stop, or some kind of kinematic equation, right? Then you can break out the 3 kinematic formulas that might look like this. Actually, we might need these in a few minutes. Okay. Right. But if you have masses and forces, then you're going to use what to figure out acceleration? Newton's second law. Right? And there's more than one way to do this. Yeah, what you got?
0.7.
I think I got something bigger than that. Bigger than what you get?
9.8.
Well, it's not going to be pure free fall because it's being resisted. Held back. What you got? I think not quite that fast. Well, it can't be more than gravity, right? Guys, it's not going to be faster than free fall, right? So it has to be somewhere between 0 and 9.8, or between 0 and 10 meters per second squared. What you got? Yeah, that's what I got. Yeah, 10/7 or 1.43 meters per second squared. All right, so Hans got it. Yeah, there you go. Right. So, you guys are definitely taking notes right now, right? Because Hans got it. Looks like everybody else was struggling with this. Let's make a 3-body diagram. So I'll do it for this block and I'll do it for this block, and then we'll figure out everything from there. Which of course is, I mean, here's the poster version, which is pretty general, but let's throw some numbers on this. Guys, what is the weight of this block approximately? 40 newtons. So I'll call this 40 Newton weight. What's the weight of this block approximately? 30 newtons. 30 newtons. Right there, right? Okay. Now, there's some other forces. There's a tension force. Ooh, guys, the tension. Is it the same tension acting on both these blocks? Yeah, we're going to say this pulley itself is massless, frictionless. So it'll be the same tension in this whole string. Okay. And the tension has to be between what and what? 30 and 40. Yeah, it has to be more than 30 to overall pull this block up, but less than 40, so that overall there's a net force down on that block. Okay, so I'm going to guess the tension is, I'm going to guess 34 newtons, right? It's usually a little bit less than the midpoint. The midpoint would be 35. So I'm going to guess 34. But we're going to figure out for sure. And the way we can figure out for sure is we can either focus only on this block or only on this block, because they'll both lead to the same answer. Okay? Yeah. Right, so, oh, whoops, we never got the acceleration first. So let's do it. Do this over here. So acceleration is net force on total mass. That's Newton's second law of motion. And no, I'm doing this from a whole system point of view. Right, so the whole system point of view, left versus right, what is the net force? 10 newtons. Yeah, because it's 40 minus 30 is 10 newtons. Right, and that's moving how much inertia? 7 kilograms. Right, 4 kilograms plus 3 kilograms gives you 7 kilograms. Yeah, that is 10 over 7 newtons over kilograms. That's about 1 point. Well, here, how about this? 1.429 meters per second squared, which is way too precise, but there's a bunch of other follow-up questions. So, okay, right. So about 1.4 something meters per second squared. Right. Again, if you use 9.8 meters per second squared for free fall gravity, you get a slightly different number. That's okay. Right. So that's the first one. What is the tension in the string? Right. So let's try it from the perspective of either individual block, and I'll show you guys that it's the same answer regardless of how you approach it. So if I focus on the 3 kilogram block, I can set up a new Newton's second law of motion, F net equals ma. Okay. But this is only applying to the 3 kilogram block. Right, you guys got that? Okay. So guys, what am I going to substitute for the net force on the 3 kilogram block? Yeah, tension up minus the weight down. Right, tension up, weight down. There's a difference there. So I'll call this the tension force, which I'm solving for, minus the weight down, which would be like 30 newtons. That's going to result in a 3 kilogram block accelerating at 1.429 meters per second squared. Wouldn't that be the case? Okay. So what is 3 times 1.429? And then add over the 30 newtons. I'm getting the tension force has to be 34.3 newtons. Oh yeah, remember how I said before I even did any math, I said I'm going to guess it's about 34 newtons, right? This midpoint's 35, it's usually a little less than that. There you go, it's like right in there. Okay. Now, what if you had picked the other block instead? I bet it's the exact same answer. Let's see. So I'm setting up another F net equals ma. Only this is going to be for the 4 kilogram block. Now this one overall is being driven downward. So I'll do 40 newtons downward minus the tension force up. Okay. So 40 newtons minus the tension force results in a 4 kilogram block accelerating at, again, 1.429 meters per second squared. Okay. Okay. So that. Okay. So little algebra shuffle later, ends up 40 minus 4 times 1.429. Okay. Now, guys, when I hit enter, there's only one number that can show up on my screen. What's the only number that can show up on my screen? That's right. It's got to be the same answer as before. Okay. Let's see if it is. Oh, yeah, look at that. It's also 34.3 newtons. It's the same thing. Same thing. Check. Same thing. All right, you guys see that? Right. All right, so keep a checklist so far. We've only answered these first 2 questions. What's the overall acceleration and what's the tension in the connecting string? Okay. And on the on your poster version, right? You guys of course have done or thumbnail version of this. Here's Newton's second law of motion in this pink box that's guiding everything. Here's the whole system solution in this gold box that could straight give you the acceleration. It's normally how I take you guys through it. Okay. And then if you want to figure out the tension, we just did each one of these green boxes individually. We did it for the left block and for the right block. Okay. And of course, they gave us the same tension. Okay. Now, keep in mind too, if you go to college, there's a good chance, I don't know, it's a coin flip. Your college instructor might actually start with these 2 green boxes and do a system of equations. It's perfectly valid to do that. you're just sort of simultaneously solving for the tension and the acceleration because those would both be unknowns. Okay, so you got two equations, two unknowns, you solve it that way. Okay, and AP also, of course, allows you to do it that way too. Okay, right. Trying to sort of focus on one method and then hammer that through, and then I mean that'll always get it for you anyway. Right? How about how fast after 1 second? Right. So here's what you know. You know the acceleration, you know the tension of the string. You guys solve. How fast is it moving after 1 second? You guys solve it. I'll solve it. Actually, I see the answer already. Right. How fast is it moving after 1 second? You can tell me. How fast is it moving after 1 second? Yeah. 1.4 meters per second. Because here's the acceleration in meters per second squared. Okay. What we're trying to answer is really a kinematic question. Guys, which formula do you use to figure out how fast after some time interval? Yeah, it's this one right here. Yeah, it sure is. And if it starts from rest, well, I didn't explicitly say that, but that's a reasonable assumption. It starts from rest, which is AT. Oh, and if you got here, this over here. V final equals V initial, which is 0 plus AT. Okay. We got 1.43 meters per second squared. We got 1 second. Yeah, it's going to result in 1.43 meters per second. The seconds. That. Okay. Is that how fast after 1 second? Okay. How about how far after 1 second? What formula are you guys going to use here? Yeah, V naught T plus half AT squared. Okay. How far is a function of time? That would be the case, right? If it starts from rest, this bit goes away. So let's do 1/2. Got 1.43. That's meters per second squared is the acceleration. And we're doing it for 1 second. Now, don't forget to square the time. Although 1 squared is still 1, but that's the only one that works out that way. 0 or 1. Okay. 1/2 times 1.43 times 1 squared. Okay. That looks like 0.715 meters. Yeah. Okay. Or 71 centimeters. You guys getting about 71 centimeters? Right. Is that? Yep. Okay. Right. We've got one more question about this classic Atwood. Okay. And I haven't quite finished the question yet. It says how fast after, and I'm going to throw a distance here. I'm going to put the distance 0.715 meters. Okay, because you know what the answer to that's going to be already, right? So, how fast after some distance? Guys, what does the answer have to be?
1.43.
Yeah, 1.43 meters per second, because this all goes hand in hand. Right? At this acceleration for 1 second, it builds up to that speed and it's moved that far. Okay, so you know what the answer is. Now, how can you show that with these kinematic equations? Which kinematic equation are we about to use to verify that?
The third one.
The third one, how fast as a function of how far. That's what the third one says, right? So let's try that. So I'll go final velocity squared equals initial velocity squared plus 2ax. Starts from rest, that goes away. So here, in terms of variables, it would look like this, right? That isn't the general solution in terms of variables. Right? It looks a lot like square root 2gh, except it's not the full g and the whole thing. Right? So square root, I got 1.43 meters per second squared. Got 0.715 meters. Okay. And you guys know this has to come out to 1.43 meters per second. Let's see if it does. So square root 2, 1.43, 0.715. Some of these numbers are rounded a little bit. Okay, so we'll see how close. Oh yeah, look at that. 1.43 meters per second. Wow, that's an exact number too. Okay, there you go. All right, guys, good. You on that? All right. Any questions on that classic Atwood? All right. So next thing I want to do with this classic Atwood is get my paper ready here. Let's actually go forward a few topics. All right, so I still got the classic Atwood, but oh look, we got a green banner now. So this is an energy. Okay, guys, go ahead and set up in your notes. What's the most likely conservation of energy setup question with that diagram? might be some variations depending on your assumptions, blah, 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 right? But it's kind of like a go-to most obvious conservation of energy setup. We're gonna do conservation of energy, right? And then what we're gonna do is we're gonna go back and hit that very last question that we just answered and see if it gives the same solution in terms of energy. Of course it will, but it's gonna test that. Okay, so everybody set up a conservation of energy for that Atwood. Conservation of energy. Okay. See if it starts from rest. Right. You let it go, it goes into motion. All right, has everybody got the conservation of energy set up? Okay. All right, so, I start this whole thing from rest, then I let it go. Okay. Now, what's sort of supplying the energy? Or here's okay. M1, M2 Earth system, if that's a question or a detail. Because the fact that we're including the Earth means we're allowed to include MGH, potential energy. Hopefully that's a term in your expression. Okay. Here's your guiding thought right here. Okay. Energy is concerned. Okay. Now, guys, what's sort of supplying all the energy to move in the first place? Yes, the potential energy in block 2. Right? The fact that the large block can fall. That's all the supply of energy. The fact that the large block can fall. Right? If you knew numbers, like you know the mass and the G and the A, maybe it's like 100 joules or something. Some number of joules, isn't it? Some number of joules. Okay. Now, on the other side of the equal sign is sort of like the demand for energy. Where did that energy go? Okay, kinetic energy for both blocks, right? And also potential energy of block 1. Yeah, isn't that 3 different places the energy is diverted? Okay. So keep track here. Right. The large block falling is supplying all the energy. That goes to 3 places. You have to lift the small block, some MGH. And then at the end of that motion, the blocks are still in motion. They're moving. So they each have that kinetic energy. Which, guys, what's the formula for kinetic energy? 1 FMV squared. And that's true for both of the blocks too, isn't it? Right. So is that what you guys wrote in your notebook? You guys with that? Okay. Now, what's probably the most obvious question that the setup could answer? Velocity of the block after some height change. Yeah. After some distance move. Okay. Which is the same thing as the last question I asked right here. How fast after some distance move? Right. So it is we must have got the answer. Oh, here it is. Okay. We got 1.43 meters per second. Guys remember that? Right. Going through the whole dynamics followed by kinematics. Okay. Now let's do the energy approach and see if we're going to get the same thing. Okay. So I got sum of energy initial equals sum of energy final. This M2GH turns into M1GH plus 1/2 M1V squared plus 1/2 M2V squared. Okay. So let's say we're solving for this V and we know all the other numbers and it matches the same scenarios we got. Okay. So I told you guys block 2 was, I think 4 kilograms, 4 kg. I've been rounding G to 10 meters per second squared. Okay. We're looking for a height change of 0.715 meters. Okay. That's going to go to, okay, lifting the small block, which was 3 kilograms, got 10 meters per second squared for also a height change of 0.715 meters. Now, this is set up in such a way, this one's falling, this one's rising. So these can both be positive. That's okay. Okay. Plus 1/2. Okay, got 3 kilogram. Moving it. Hey guys, it's okay if I factor out the v squared from these 2 terms. Is that okay? Can I factor that out? Right. So let me do that. So 1/2 3 kilogram plus 1/2 4 kilogram. And then out of all that, I factor out the v squared. Okay. Right, like that. Okay. Right. You could solve this in terms of variables. We'll keep going, but let me get some hard numbers here. So it's 4 times 10 times 0.715. So this is 28.6 joules. There were 28.6 joules ever in the system. Okay. If I pop in a 3 here, it looks like 21.45 of those joules went into lifting it against gravity. Okay. And then here I have, well, half of 7 is, so plus, now this would be 3.5. The unit turns out kilograms, and then I got this v squared, and I'm solving for v. Okay. All right. Oh, it's easier to handle algebraically, right? Okay. Okay. Everybody gets so far. Everybody good. We're good. Okay. All right. So we're gonna take the supply of energy, subtract off this 21 joules, so 28.6 minus 21.45. Okay. I have 7 joules left over to go into 1/2 mv squared of the combined blocks, if you think of it that way. V squared. So last 2 steps, can I divide over the 3.5 kilograms and then finally take the what? Square root. Yeah. So divide by 3.5 and then take the square root. I'm getting to 8. You go, oh, look at that. Look at that. 1.43 meters per second. There you go. I mean, that had to be the answer the whole time. Because that's also what we got going through dynamics followed by kinematics. And this is the energy approach, and it's the same thing. Okay. All right. Are we good? We're good. All right. So there's your classic Atwood. Classic Atwood. All right, ready for next one. Oh, it's a modified Atwood. Oh, look at that. So, give you guys a scenario here. All right. Let's say this top block is like 50 kilograms. And it's tied by a string to a little block here that's like, oh, let's do 2 kilograms. 2 kilograms. How about that? Okay. Got a massless frictionless pulley. Okay. Here, I'll put this on little tiny wheels right here. Just get rid of the friction, right? But maybe not significant rotational inertia though. Okay. So, what is the acceleration? Well, I'll just say acceleration. Right, you guys get it, right? Downward acceleration of the falling block or so on. Okay. What were the other questions there? Okay, what's the tension in the string? Tension and string. Okay. Acceleration, tension, and string. Okay. How fast after 1 second? How far after 1 second? Okay. And then I'll say how fast after. How fast after. Okay. And then just like before, we'll take whatever the answer to this how far question, we'll plug it in there, and then we'll switch over and do the energy part of this. Right? So this is pretty similar setup, but a little bit different. Okay. So 2 kilograms versus 50 kilograms. Okay. I'll solve it. You guys solve it. All right. I have the acceleration on my screen. Who else has got the acceleration of that system? Who knows? What is the downward acceleration of the 2 kilogram block? Or the horizontal acceleration of the 50 kilogram block? Because of course they're the same acceleration. They're tied together. Okay. Does anybody know? Aha, there you go, 0.4 meters per second squared. Aha. Okay. So got that by, guys, how much does the 2 kilogram block weigh? 20 newtons. And that would be the net force, wouldn't it? Okay. So 20 newtons. And how many kilograms total is being moved by those 20 newtons? 52 kilograms. 52 kilograms. Got a 20 Newton weight pulling 52 kilograms of inertia. That divides out to 0.38 meters per second squared. Okay? All right, guys good? Okay, here. So I got, here's Newton's second law of motion in general. Here it is as it applies to this puzzle. And that's what we just did. We just did that gold box right there. We just did that gold box. Okay. Now, if you want to get the tension in the string, here, see if you guys can figure out. I'm covering up a couple of formulas that are going to be in green boxes. And they both will tell the tension in the string, but one's from the point of view of this top block and one's from the point of view of this hanging block. Can you guys write those 2 equations? Go ahead and do that. What 2 equations am I covering up right here? Go ahead and write it in your notes. Right, both of them. And they both look sort of like Newton's second law of motion. Right? So they fit that format of Newton's second law of motion. But they apply to either this block individually or this other block individually. Okay, that's the 2 equations. Okay. All right, you guys got this? Right. Who can tell me? Guys, what's one of the equations you just wrote?
We're trying to have 2 acceleration times now.
Yeah, there you go. If I take the difference between these 2 forces, right, this weight down minus this tension up, because now we're getting into the tension. Okay. That net force is equal to M times A for the hanging block. Is that this one here? Yeah, that is that one right there. Look at that. That's exactly that first one. Okay. We didn't know which one I took first. Okay. And then what does the Newton's second law equation look like for this other block? What's the net force on this block up here? Just the tension. That's it. Just the tension. Right? I've got friction grayed out like it's negligible or some little wheels. So we're going to say there's no friction up here. Now, there's a variation. You could put it there, but let's say just the tension. Now, there are a couple of vertical forces, but those just zero out vertically. Okay. So the tension is the net force. And the tension is moving how much mass? Only M2. There's your second equation right there. Okay. And if there was friction, you subtract that out, but we're going to say there's no friction. So it's just F2 equals MA.
So if it's all behind, you just pass on top of that. The string connecting another block.
Oh, okay. So you're saying what if here, I draw it here. You're saying what if the string was connected and there was like another block here also on wheels? Yeah. Okay. So if there was something like M3 here, then yeah, this string has to pull the combination of both of these masses. Yeah. Okay. Now this connecting string only has to pull M3 behind it. So this tension would not be as much as this tension. Right? Okay. But we're gonna get rid of that. Okay. All right. So what we came up with acceleration is 0.38 meters per second squared. Okay. The tension of the string. So let's say I do this block here. I got 20 newtons down. I got some F sub T pulling up. In fact, I bet they're pretty close to each other. I bet this tension is just a little bit less than 20 newtons, maybe like 19 newtons or something like that. Okay, because this block is going to be accelerating very slowly. So there's a very tiny net force on it. Okay, so let's do it's right here. Net force results in mass times acceleration. The net force would be 20 newtons down minus the tension force resisting that is the 2 kilogram block accelerating it. And now I know how much the acceleration is because we just solved it from a whole system point of view. 0.38 meters per second squared. Right? Is that okay? Okay. Then little algebra shuffle. What's 20 newtons minus and then 2 times 0.38? I'm getting, oh look, it's just what I said it should be. About 19 point something newtons. Okay. Right, you guys see it? About 19 something newtons. Right. Now you could have done that instead from the point of view of this 50 kilogram block. You should get the same answer. Let's see if I do. So I'll go back to net force equals MA, but I'll do it for this block instead. So this would be the tension force. It's pulling it. It's got 3 forces on it. It's got its own weight down. It's got a normal force up. This cancel out, whatever. And here's the one I really care about is the tension force, and that is the net force on the top block. That's going to be 50 kilogram block accelerating at, oh, and again, just this number right here, 0.38 meters per second squared. Right, guys, yeah. So what is 50 times 0.38? Oh, look at that. It's 19 newtons. Now some of these numbers are rounded a little bit. That's why it's not super exact match, but yeah, 19 newtons, 19 newtons. Guess it? Okay. All right, guess good. Guess good. Okay. What else was I asking? How fast after 1 second? So that's a kinematic question. Kinematic. Can you guys go V equals V naught, which is 0 plus AT? Okay. So we're doing 0.38 meters per second squared for 1 second. Is that 0.38 meters per second? Right? So that's how fast after 1 second. How far after 1 second? Isn't that the V naught T, which is just 0, plus 1/2 AT squared, right? 1/2 AT squared. So that's gonna be 1/2. I got 0.38 meters per second squared. We do this for 1 second and square the time. Okay. So 1/2 times 0.38. I'm looking at 0.19. And guys, what's the unit on that? That's 0.19 what? Meters. Yeah, because it's a distance. That's about 19 centimeters. Hey, I got 19 centimeters right here. Here's 19 centimeters. About 2/3 of the ruler. That's how far I moved. Right, you guys good? Right, now last question. How fast after? I'm gonna put 0.19 meters. That go off the paper. Oh, no, that's on paper. Okay. Okay. Now, you guys know what the answer is gonna be. Guys, after it moves 0.19 meters, how fast is it moving? 0.38 meters per second. Because both of these correspond to 1 second. That's why it's all got a line. Okay. But we can pull up the first kinematic formula. Speed squared equals initial speed squared plus 2ax. That's all that way. Okay, sorry for brass, that goes away. So we're back to this. Square root 2ax. I got 0.38. That's meters per second squared. And the distance was 0.19 meters. Okay, take a square root of all that. And I better get 0.38 meters per second. Right, that's got to be the answer. So it's the square root of 2 times 0.38 times 0.19. Yeah, that's exactly it. 0.38 meters per second. Okay. All right, guys, good? We're good. Are we good? All right. All right, guys, ready for our next poster? Next poster. So it's, hey, it's the same picture. Only this time, let's skip over and do some energy. Okay. So when I say energy, you guys are thinking like all that stuff right there. Okay. So I need the 2 blocks in the system, and I also need the Earth in the system to be allowed to consider MGH, right? Gravitation potential energy. Okay. So here's my framework. Energy is conserved. Guys, go ahead and set up probably the most obvious conservation of energy setup for that scenario. Can you guys do that? All right. Now we have a few minutes left, but I think what I want to do is just kind of walk you guys through this way. Guys, what you guys write? What's sort of the supply of energy?
M1GH.
Yeah, M1GH. Yeah. So this block falling. And where does that energy go? Yeah.
It goes into moving the second mass and then maintaining both of their speeds.
Yeah. So both of these blocks are going to have a kinetic energy after that motion. Right? But that's it. Because this other block isn't being lifted. So this other block doesn't change its potential energy. Right? But it does change its kinetic. There you go. There's a whole setup right there. Okay. And of course, you could plug in numbers and get exact solutions to exact questions. Okay. You guys come up with that conservation of energy? Okay. All right. Ooh. You guys remember this one? So yesterday I had you guys derive some incline equations, and today we were focusing on Atwoods. And here it is all together. We got the incline, we got the Atwood, we got it all going on. Okay. Now, a good question could be something like, if I want you guys to see the big picture of this. If you see the big picture, then any question that gets thrown your way, you can figure out how to work in the details. Okay. So this block has, I see 4 forces on this individual block. It's got the weight down, which I can break into components, which will be helpful later. It's got this normal force, it's got this tension force, and it probably has a friction force too. Okay. Now this individual block has 2 forces. It's got its own weight down, it's got this tension force back. Guys, is it reasonable to say that this tension are the same tension? Yeah. Now I would probably start this from a whole system point of view and start getting the acceleration. So here's what I see as the net force. I see the weight of the hanging block here says, let's go clockwise. Guess what forces are resisting that? Yeah, this friction force. And also this mg sine theta. In fact, that's exactly the setup here. The net force is, here's this purple force saying, let's go clockwise. Here's this green force, or fourth component, really, and this friction force saying, no, resisting that counterclockwise, right? Now, the friction force only points down to the left as long as it truly is rotating clockwise. And if it wasn't, if I guessed wrong, then I'd have to swap the direction of the friction force. Okay. So if you're told coefficient of friction, can you calculate the friction force based on the normal force? Yeah, so you might work in that way. Or if you know something about the acceleration of the system, you can back calculate what is the coefficient of friction, and maybe that can be the question, right? So there's lots of ways you can go with that. Question. All right, so you guys go with that. All right, that's a pretty good pause point here today. All right.